Hello everyone and welcome to Mind for Physics. This video is about vectors. So the previous video to this is kind of a part one. Physics goes in a very specific order, so you have to watch that video before you watch this one. Okay, so the purpose of this video is to draw a distinction between abstract and real. So as you can see, this is a very conceptual video. When I first learned about vectors and started using them and solving problems using vectors, I had no idea about any of the information I'm going to cover in this video. And I thought, what a detriment. I think that this is where things should begin. So that's what I'm trying to do in this video. There are things that are abstract that we come up with, we create to represent or stand for real things. For example, numbers are abstract symbols that we came up with to count things that do exist in a natural world in which you and I live in. For example, trees and cows. We count those using numbers. So numbers are abstract and cows and trees are real. Vectors are abstract and forces are real. So the way I'm going to explain this is going through the same argument twice. First for numbers, second in the second part for vectors. The main point of this video is to really crystallize exactly what a vector is and why we need them and what power it gave us. But I'm going to start with a tangent and tell you about numbers because we are more familiar with numbers. We've been using numbers our whole life. Vectors are kind of new because they only come in physics, right? So I'm going to begin with numbers. So first and foremost, why did we come up with numbers? And yes, we came up with numbers because we're the best. We came up with numbers in order to count real things like trees and cows. So numbers are abstract and cows and trees are real. Abstract things live in our head. Real things live in the real world. If we disappeared tomorrow, vectors and numbers would disappear with us, but cows, trees, and gravitational force would stay. So this happened a long time ago, 5,500 years ago in ancient Mesopotamia. People first started counting. And there was a natural need to do math. There were very human problems that needed to be solved using math. For example, imagine I was an ancient grandmother in ancient times and I completed life and I was dying. I would have to write my will. Here's me writing my will. If I had 5 kids and 10 cows, I would have to do a little bit of math to decide how much I'm going to give each child. So math came with its own rules. Even if I really wanted to give each child 3 cows, that would add up to 15 if I had 5 kids. And I could not magically come up with 5 extra cows if I only had 10. So we do not get to boss math around. Each child would have to get 2 cows, and that is called algebra. That is, it seems unfair because we came up with numbers, and it seems fair that we would dictate the rules of mathematics, but it's not the case. Algebra is its own set of rules, and we have to respect it. Okay, so it all ended in algebra. So let's start this whole argument and build it for vectors. So let's take a moment to appreciate the amount of procrastination that happened between 3,500 BC to 19th century. So we came up with numbers when human beings were pretty much unclothed, running around naked, and vectors, happened so recently. These two gentlemen are credited to have come up with vectors. So let's kind of summarize everything that we know about vectors and numbers this far. So neither of them exist in the natural world. Vectors and numbers both are abstract symbols and ideas that we created, and they're there to represent or stand for stuff that does exist in the natural world. In the case of vectors, forces, accelerations. In the case of numbers, we use numbers to count cows and trees. So vectors are abstract and forces are real in this case, electromagnetic force, but it could be gravitational force. Just for, I mean, if a physicist watched this video, they'd be like, there are not all these forces that I'm going to show you in a second. There are 4 fundamental forces: electromagnetic, gravitational, and weak and strong nuclear forces. Those 2 nuclear forces cannot be experienced on a human scale, but gravitational and electromagnetic can. Just forget what I just said. That's so that people are not like upset with me. But let's just think about really everyday type of forces that we do get to see with our own eyes. For example, a basketball will float in a water because there's some type of a force that does for real exist there, that's pushing it up, that's allowing to float. The first force is weight. The heavier the object, the longer the spring will stretch. That's weight. The second example is frictional force. That force that fights motion, that's an example of force that exists in our natural world. Like you deal with that all the time. You slow down on sand faster than on ice. That's because of frictional force. That is a real thing. So another one is electromagnetic force, like with in the case of a magnet. You've, I'm sure, played with that, so that is such a real thing. You get to experience it. Another family of vectors is acceleration, is a vectoral quantity as well. So acceleration, you're familiar with that as well. It's like when your car accelerates, it has direction and magnitude. Sometimes you accelerate too much, right? When you jump out of a airplane with a parachute, you are always moving downward and with a specific acceleration of 9.8 meters per second squared. Another type of acceleration is centripetal acceleration. Any object that's going round and round and round is going to experience centripetal acceleration, pointing towards the center of that path, circular path. So for this video, let's focus on acceleration, specifically gravitational acceleration, the one that kills us, right? The gravitational force kills us. There's acceleration. That's one of the most popular accelerations that we have to kind of confront in our daily lives. If you jumped out of a building, you would have acceleration pointing downward. Snowflakes each snowflake has acceleration of a specific magnitude, and which is 9.8, and specific direction, which is downward. Okay, what's the problem with this acceleration? It's a real thing. It exists in the natural world, and we have nothing to represent it. And no, number is not good enough. We need something else, because number can only tell us about can tell half the story. It can only stand for 9.8 portion of the gravitational acceleration. But what about the direction? Like apple always falls down. What about that down? I have nothing to represent that. So there was that problem that needed to be solved, and it wasn't solved for so long. We needed answers. There were no answers until we came up with vectors, which was 200 years ago. The birth of vectors is very recent. Vectors length represents its magnitude, and it shows you direction. So it kind of took care of everything, right? Direction and magnitude. So all was really great with the world after we came up with vectors. Similar to numbers, vectors came with their own set of rules. That's called vector algebra. And you know how useful it is to use numbers to do math, like I just showed you, like very practical, everyday human type of math? That's exactly how useful vectors are to do vector math, to add vectorial quantities. If you added vectorial quantities like force, like you add numbers, you'd be committing 2 mistakes, 2 errors. First, that you assumed that force was a number or scalar when it's not, it's a vector. And then to kind of treat it and add it using number addition rules instead of vector addition rules. So it wouldn't work out. The science wouldn't work out, right? You have to do right things, otherwise science doesn't work out. So this is a very common everyday problem. If you have an object and every single family member decides to push on this table. So far, we just have one little human being pushing it with a small force. The force is pointing west. So the resultant vector here, the overarching force that's applied to this table is coming from this boy alone, because there are no other humans so far. But if you had another person exerting a larger force, that refers to magnitude, in the same direction, then you would have to add these two forces. So you need some type of vector addition rule here. So you would add these forces, and this would be the overall force that the table would experience, right? If you had a third person pushing against, now you need vector subtraction, okay? It's still in one dimension. Two people are pushing it left, westward, and one person is pushing it right, eastward. Now, if you had a fourth person pushing it out, now you have a two-dimensional problem. You have vectors in two dimensions. Again, you need to have rule to add these because it looks like a chaos, right? Now, if you have a fifth person trying to push it up or lift it up, lift the table up, now you have vectors in three dimensions. And don't you worry, because you have vector algebra and you can add these vectors. And this would be the green vector would be the resultant vector. And in the coming videos, you're going to learn exactly how you add vectors in 1, 2, and 3 dimensions. But all of that was not possible before we came up with a vector. And vector is not real, forces are. That's all I wanted you to kind of start thinking about in the beginning of your semester so that you can enjoy physics more. Thank you so much for watching this video. I hope it helped. We are done. You can throw your books away, and goodbye.